Hey, everybody. Yeah, my name is Amar, and I'm a software engineer on the pricing team at Lyft. And I'm going to talk to you today about dynamic pricing, which I'm going to use interchangeably with primetime for the rest of this talk, and how we're transitioning to using Beam and Flink to compute it. So as far as an overview of what this talk is going to be, I'll start out by motivating primetime, explaining what it is and why we need it. And then I'll talk about our existing infrastructure, how we actually compute it, and why we actually want to move to a streaming architecture and what that looks like. And then I'm going to save some time to talk about some lessons we've learned. This is very much a work in progress for us. This is kind of an active project that we're working on, but already we've learned some things that hopefully will be of interest. So with that said, what is primetime? Some of you may already, hopefully a lot of you are familiar with this, but if not, the idea is it's a multiplier that applies to the fare that we charge you for a ride that is tied to a specific time and place. And as far as place, we use what's called a geohash system to identify places. You can think of it as just a sort of grid imposed on the world map. And we use geohash 6 precision, which sort of equates to a couple of city blocks wide. But basically, for a given geohash 6 at a given minute, the prime time is a multiplier like 2.0. And so why do we need to do this? A common misconception that people have is that prime time or congestion pricing, surge pricing, call it what you will, is something that we do in order to make money or to extract profit at times when people need rides and there's a lot of demand. But it's actually not true. Prime time is primarily means that we have to balance supply and demand. So to think about why we need to do this, as you can imagine, the marketplace for Lyft and for ride sharing is constantly changing. You know, there might be a storm, there might be a concert that lets out, and we often run into situations where our supply, meaning the drivers we have available in a given time and place, is outstripped by the demand. So if you think about what happens when supply is outstripped by demand, there's a few problems. One is that as more and more people kind of are picked up by drivers and we run out of drivers, the time that it takes other people who are requesting rides to get a driver goes up and up. We call this the ETA, the estimated time of arrival. And eventually it goes up to the point where people just give up. They're no longer able to get a ride, which obviously is not a good experience. Another problem that we can have is if you've got a lot of drivers over here, whereas you've got a lot of demand over here, without us constraining the demand in some way using surge pricing, what ends up happening is these people over here request drivers that are pulled from an area far away where there is supply. And those drivers spend an increasing amount of time not giving passengers rides, but just driving around to where the passengers are. This is known as a wild goose chase, and there's actually an interesting paper about this. I'm not going to go into too much of the details on it, but you can Google it. It's called Surge Pricing Solves the Wild Goose Chase. And this paper just talks about how in any ride-sharing system, this is a failure mode that you need to address, and congestion pricing or prime time is just an effective way to do it. So that's what prime time is. So let me talk about our current infrastructure that we use to compute prime time. So I'm not going to go into a super level of detail here, but essentially we have a series of, you can think of it as cron jobs. We have a series of jobs that run on worker machines that start up every minute. And this is essentially a directed acyclic graph, although as I'll get into later, it's not currently represented in a way that is easy to parse. But what happens is we take in events from clients, where a client would be the Lyft application on a passenger's phone or the driver application on a driver's phone. And then we take in a very high volume of these events constantly. Like whenever you open your Lyft app, it's periodically pinging us. And then similarly, if you request a ride or cancel or are dropped off, we get events for those things as well. So we take in all these events and we aggregate them We deduplicate them and do other types of processing. And then we compute features based on these aggregated events. So we start out with things like unique users in a given geohash at a given minute. And then we proceed to things like, what is of the users that exist in a given geohash, how many of them are actually requesting rides? What effect does the prime time have on the rate at which people request rides? How many drivers do we need to have in order to maintain a certain ETA level? And then we finally write all this. We then feed this all into primetime models, which are, TensorFlow or Pandas models. It's kind of a mishmash of things. And these models compute the prime time, which we then write to Redis. And you can see at the bottom here an example schematically what that looks like. Basically, it's for a given region and a given minute. We have this dictionary of geohash to multiplier. And region, so we kind of had to pick a level of sort of distribution for our work, and we choose a region level abstraction. So a region is something like New York City or San Francisco. And our workers, when they spin up every minute, pick a region, and we use Redis to kind of lock regions to ensure that multiple workers don't process the same region. That's how we distribute the work at the moment. So it's basically working. I mean, obviously, you're able to take a Lyft ride, primetime work. So why do we want to transition to a streaming architecture? So there's a few problems with our existing architecture. One is latency. And so to dig into that a little bit, because we have these cron jobs that spin up every minute and only on the minute, we run into a problem where, say you've got some worker and it's computing some feature, and the worker only takes 5 seconds to run. And then you have something further down in the pipeline that takes this feature as an input. It can only proceed once it's received that input, and that doesn't happen until it spins up in the next minute. So you have this problem where you have these kind of cascading dependencies that result in the actual time between when an event is observed and the time when it is reflected in the prime time being as much as several minutes. And obviously, for our business, we want to have as reactive a system as possible. If a concert gets out, we want to quickly react to that and adjust prime time to suppress demand as needed. So we're very interested in kind of building more reactive models. Another problem that we have is code complexity. So when we wrote our code, and some of this predates me, we kind of hand-rolled a lot of the features around aggregation and windowing. We have kind of a complex Redis-based scheme for storing events that are aggregated on a minute and 5-minute basis. And it's not necessarily easy to change the aggregation units. Or if we want to do something like move away from region-based computation to kind of distributing work on a, say, sub-regional level or on some other level, it's not easy to make that change. And finally, we're pretty bound to this notion of sort of workers spinning up as cron jobs periodically. And so it's difficult for us to do something like sort of compute prime time on demand or as events come in. So if you wanted to do something like in a place where things are changing rapidly and we're getting a lot of event influx, sort of compute prime time more frequently, whereas in some place like Wyoming where there's not much happening, compute it less frequently. That's not something that our current system supports. So Thomas talked a bit about Beam, and Tyler talked about the streaming architecture in general. And this is a good fit for us. This is kind of the stack that we're moving towards. Beam was definitely important for us because we're a Python shop, and we don't necessarily want to rewrite a lot of our code in Java. We don't have the expertise or necessarily the interest. And so with Beam, it's pretty sweet because due to the portability aspect of it, we can just sort of rewrite our existing code to use the streaming architecture without having to rewrite all of the methods and models and stuff that we use. And we're not currently on Kafka. As mentioned, we're still using Kinesis, but we do have a plan to eventually migrate to that. So this is what our stack is eventually going to look like, and is starting to look like now, except for the Kafka part. And I'm going to talk a little bit more about the details of that. So, very conceptual outline here, what our new pipeline looks like. As I mentioned, we have these events coming in from Lyft apps, things like ride requested, app opened, ride canceled. So this is the source of our directed acyclic graph. And then we take in all these events and we do various types of filtering. Lyft is a microservice architecture, so this filtering involves calls to other services internally. And we're doing things like, because we're getting these pings constantly from apps, we need to dedupe in order to get unique users. Some of these pings might be from drivers, so we don't want to include them in the counts for demand. So we do all these types of processing and then aggregate and window, which Beam kind of provides out of the box, which is nice, to get features like unique users per minute, requests per 5 minute. And then finally, we run our data science, TensorFlow, machine learning models to generate the features I mentioned earlier, conversion rate and things like that, and then feed them into our primetime models, which finally we end up with the multipliers per geohash 6 per minute that I mentioned earlier. I'll leave time at the end to answer questions. I know this is pretty high level, but hopefully that makes sense. And we're definitely making use of some of the features that Beam and Flink provides. I mean, it's really nice that aggregation and windowing is kind of handled for us. So it really reduced the amount of code that we have in our pipeline significantly. And we're triggering computation via watermarks. Do you guys know what watermarks? So I think a way to think about it is it's like a function that maps, I guess, processing time to event time. So it basically says, at this given point in time, we estimate, the system estimates that it's seen all the events up to this point in time. And so we can, because there's a natural lag between when an event occurs and when the system processes it or registers it. So we can basically use this to trigger computation when the system says it's observed all the events up to some given period, as opposed to just triggering periodically based on processing time. And then we just wrapped all of our machine learning models and our internal service calls within Beam operators, which is actually pretty straightforward. And then we still just write it to Redis like we did before. So this actually was not too, it didn't take as long as I thought it would to accomplish this, although we're not fully there yet. We started with some proofs of concept because we weren't even sure if some of this was going to work. I mean, what happens when we make these in calls to our internal services from within Beam operators? Are we going to be able to run our data science and machine learning models from within these Beam operators? Is this going to even sort of process stuff efficiently? But once we had fleshed out those proof of concepts, it didn't take too long to port all of our code, so that's done. And we're currently running some production tests in different regions to just make sure that the prime time that we compute with this new streaming architecture doesn't have any sort of negative effect on our business metrics. We would expect the opposite, actually. I mean, the hope is that this is going to be a much more reactive system, and we're actually going to see improvements to some of these metrics. But even aside from the business metrics, adopting this framework kind of gives us a framework to sort of more rapidly iterate, produce new features, and it also just makes the code a lot easier to understand. And so, as I mentioned, we still have some work to do on the productionization story, and I'll talk a little bit about that under lessons learned. We've yet to move to Kafka, although it's in the works. And there's a newer feature of Beam, stateful processing, which is basically where the nodes that are doing the computation within Beam can sort of keep some state. And this is going to allow us to further simplify our pipeline, but we haven't made use of that yet. So lessons learned. There are a few things we've learned. And the first big one is that shuffles are not free, and you got to keep things simple. So what do I mean by this? Basically, when we started out porting our pipeline to Beam and Flink, we sort of naively assumed this is some high-performance streaming framework. We don't really have to worry about how many aggregations we're doing, how many group by keys we're doing, shuffles, et cetera. It's all just going to be fine. But in practice, that was not the case. And so in Beam, you have this notion of task managers, which is basically like the Java processes that you actually farm work out to, the distributed work out to. And each of these task managers has what's called a network buffer, which is a part of the JVM memory that's reserved for handling network operations and transferring data between nodes. And it turns out that the network buffer usage scales quadratically with the number of shuffles you do. A shuffle here is just any time you are doing something like group all these events by region and then do some processing on them. And we found in practice that when we were up and running with our pipeline, it was too complicated, and we would quickly just run out of memory. It wasn't able to keep up with the event ingestion that we expected it to, and we had to spend some time actually going through and simplifying it. The advice that we got is basically you shouldn't do an aggregation on a given type of key more than once. And again, this is where the stateful processing is going to help us a lot, but it's still something we're actually working on. And I had kind of a before and after slide that showed you an example of where we're at with the simplification of the pipeline, but we're in what's called a quiet period, and they told me to leave those slides out. So, memory. So, I guess with Python, one of the nice things is that you don't necessarily have to spend a lot of time thinking about garbage collection and memory usage. A lot of times, things just work. But then when it doesn't, it's definitely important to kind of understand how you can track down memory leaks. So in our case, once our pipeline was up and running, we found that over time, the memory usage would slowly and steadily creep up to the point where we got an OOM and just the pipeline died. And it took some kind of research for us to figure out how to figure this out. And one of our engineers on the team, Rakesh, is actually going to put out a Lyft engineering blog post about this. But it boils down to just understanding how to use tools like Object Graph and PSUtil and be able to sort of trace allocations and where the bulk of your memory usage is happening. In our case, we found a couple of things like there's this data analysis library called Pandas that we use pretty heavily for our data science models. And it turned out there was a memory leak in the indexing code for data frames. And there was also a problem with Beam itself, which I'll get to in lesson 4. But yeah, it's definitely important to kind of be able to profile things for a long-lived pipeline. And related to that, you should really instrument everything. I would almost hope this is obvious to everyone. Observability is super important. And we knew this, yet at the same time, we found that we were lacking certain stats that we actually needed. When transitioning between an old and a new pipeline, it's super important to be able to compare at each stage what's happening in the old and the new versions of the pipeline. And in our case, we found that with the new pipeline, once we had ported all the code, we would run it for a while, and we noticed that the demand that we computed for a given region, the unique users per minute, would slowly start to decline over time. And we spent a lot of time trying to figure out why, and couldn't really figure it out because this problem would manifest before we had even done substantial transformations on the incoming data. And eventually we were like, okay, well, let's just instrument at the Kinesis ingestion point in both the old and the new pipeline. Let's count exactly how many events of each given type we're seeing at each point in time. And it turned out that the reshuffle operation in Beam had a bug that was dropping some events. And it's just not something that kind of occurred to us initially that there could be a problem in reshuffle. But if we had just instrumented the event counts from the get-go, it would have been a lot quicker to catch that. And similarly, because it can be hard to diagnose problems when they do occur in a Flink pipeline, it's super important to have stats kind of at every intermediate stage of that pipeline that lets you know how many intermediate results are you computing, what are the values for those results, and be able to compare that for the old and the new system. Python Beam on Flink is alpha. Not a bad thing. I mean, it's pretty awesome that this technology exists, as Thomas was mentioning. It's come a long way, and it's what enabled us to sort of move to a streaming pipeline to begin with. But with any alpha system, there's going to be some issues. I mentioned that there was a problem that we found where events were getting dropped with reshuffle. There was a problem with memory leak. We did find that all these bugs got fixed pretty quickly once we reported them. So it's not necessarily a bad thing. It's just that you have to be in touch with the community and be able to sort of create a sample test case that illustrates the problem as soon as you find it. And Flink is pretty mature, but using the portable runner and Python Beam on Flink specifically, there's a little bit of kind of alphaness to it. Although I'm sure it's going to solidify over time, and it already has quite a bit. And the community is very helpful. And finally, this is another thing where I guess it's obvious, and yet it's still something we're trying to figure out, is you really have to figure out what your staging and deployment story is going to be for a long-lived streaming pipeline like this. In Lyft's case, our microservice architecture, we sort of have like a well-established set of processes for deployments where you deploy to staging, and then you deploy to a Canary box, and you make sure that there's no problems on Canary, and then you roll out to everywhere else. But that whole story is not necessarily going to work for a long-lived Flink pipeline. So we're still thinking about what's the right way to kind of deploy a pipeline change, and how do we handle downtime? How do we handle incomplete windows where we don't, we haven't processed all of the events in that window? And this is complicated by the fact that we're also moving to Kubernetes, and so I don't know. I think you definitely want to kind of go into it having a sense of how you're going to handle deployment and how you're going to handle testing. Short wish list. Some of the Beam features we found could maybe use a little bit better documentation. Like we're trying to use the stateful processing feature, which is pretty useful, but our engineer who is working on it is mainly just going off the actual PR that was committed, because I don't think there is other documentation. KV logging is a pretty minor thing. I mean, we just have this way of logging at Lyft where we have sort of key value pairs that we emit logs for, and then it's just easily accessible in Kibana. I think that's just some Apache configuration, but it's not necessarily built in. And just in general with Flink, I found that we get a lot of these arcane Java stack traces where it's not always clear exactly what's happening. So I don't know really what the answer is there, but it would be nice to have a little bit better of an ability to figure out when problems do occur, where they're happening. We are hiring. You probably knew this, but I find a lot of people seem to be interested in machine learning or streaming. And dynamic pricing in primetime is actually a pretty cool intersection of these technologies. You really get to have a huge impact in the sense that pricing is crucial to our business, and any sort of improvements or changes you make to this part of our infrastructure really has an immediate impact. And there's kind of lots developing at Lyft with respect to streaming and pricing. I mentioned that we're integrating with Kafka, and we're trying to just scale out to all regions. We're starting to use GPUs more heavily, particularly for our TensorFlow models. The GPU story is going to be very important. And just in general, throughout Lyft, we're finding more and more places where a streaming architecture might make sense. And so there's going to be a lot more use of it going forward. And also, I sincerely believe that ride-sharing is making the world a better place. And working at Lyft is pretty cool in that you do feel like the work you're doing makes a difference. I mean, for things like city planning, moving away from a sort of car-centered philosophy of city design, with respect to emissions, with respect to all kinds of things, I think you feel pretty good about working here, or at least I do. And if you are interested, feel free to email me or my manager at the email addresses mentioned. I think there's also that careers link that Thomas mentioned in his slide.